Welcome everyone to the celebration of the Foundation Day of the ICTS. Uh, every year, of course, as many of you in the ICTS community know, we have a Foundation Day lecture by an eminent scientist. And this year were thinking what to do, and we had canceled many of our special lectures, but then many of the people in the ICTS community were organizing a cultural program, and as you know, there will be the program will follow this lecture. So then we thought we should maybe go ahead, and even though we also have a nice dinner afterwards, though we can't do that virtually, we thought we will at least go ahead with having a lecture. I must say, at a very ridiculously short notice, Professor Herbert Spohn have very kindly agreed to give this lecture at ICTS. Many of you at ICTS know Herbert very well. He and his wife Sian have been to ICTS several times, the new campus before, and in many of our programs. They have spent an extended period of time here, and I hope once the pandemic is over, both of them will come and again spend a lot of time with us. So having that degree of comfort with Herbert, we decided to approach him, and since he is an ideal candidate for the Foundation Day speaker, we approached him, and hence we have this lecture today. So once again, my thanks to Herbert. I will now maybe, so as you know, the program, we'll have the lecture, and then there'll be a short break, and then the cultural program by members of the ICTS community will be afterwards. Those of you who are not from ICTS, you're welcome to join for the cultural program as well. There's a lot of nice talent in the ICTS community, which you will see here. But I'm very happy. One positive thing about the, I guess, going virtual with the Foundation Day lecture is that I see many people who are not from ICTS who have joined as well. So that's one of the pluses of having a move to this virtual mode. So let me now hand it to Abhishek to introduce the speaker formally and get the lecture going. Over to you, Abhishek.
Yeah, thanks, Rajesh. It's a great pleasure to have Herbert here, and it's a great pleasure to introduce him. So, like Rajesh said, I mean, many people in ICTS already know Herbert very well. So, but let me give a formal introduction. So, Herbert Spohn is emeritus professor of excellence at the Technical University in Munich. So his area of research is non-equilibrium statistical physics and mathematical physics. And he's made important contributions in several areas like stochastic interacting particle systems and lattice gas models. So there's the famous KLS model is named after, so he's one of the authors of this paper. Then he's worked on open quantum systems, again, important works on systems like the Lindblad equations and so on. Determinantal point processes and random matrices, and then related to this, the dynamics of interfaces, where he's again, where Herbert has important works on the KPZ equation and in particular understanding fluctuations in this system. And then, I mean, more recently, some of the important work of Herbert is in the area of fluctuating hydrodynamics, and so where of anharmonic chains in particular in 1D systems. And in this, he developed a new formalism which allowed one to understand anomalous transport properties of one-dimensional interacting systems. And this has been applied recently to extended to quantum systems, and it's a really very exciting area. And then more recently, he's been working on this area of generalized hydrodynamics, and that's what he's going to talk about today. Herbert has written two very important books. So one is on, I think, dynamics of charged particles and the radiation field, and the other on interacting particle systems. So Herbert has won a large number of awards. I won't name all of them. But his most recent award is last year. He received the highest award in statistical physics, which is the Boltzmann medal. And in fact, he was in ICTS at that time, and we had a celebration. So, I won't continue. I think we can start Herbert's talk on generalized hydrodynamics. So, Herbert.
Okay, so thank you very much, Abhishek, for these kind words. And Rajesh, I mean, I'm very pleased for this invitation and thankful for this opportunity. Now, this is sort of a general talk, and the first thing I tried to do was just to think about areas where hydrodynamics comes up. I mean, you know, the title is Generalized Hydrodynamics. So let's first look at hydrodynamics, which sort of, I think everybody knows more or less. And so I came up with a few things, and let me just share them with you as a kind of introduction. I have to, wait a second. First I have to, no, this doesn't work this time. Why can, no.
Sometimes.
Yeah, that's okay, that's okay. Okay, so of course, I mean, it's sort of, you know, when you Google, when you think about what you learned, I mean, of course, it's everywhere in physics. So I just put a few items, and I should start with the one of Euler, I mean, which is an absolutely remarkable sort of achievement. I mean, he was able to write down the hydrodynamic equations, I mean, what we usually call fluid dynamics for simple fluids. So these are neutral fluids, I mean, made up of simple molecules or atoms. And the amazing thing is that you know, I mean, there's a lot of, I mean, reasonably sophisticated mathematics associated with it. And of course, it was not present. I mean, you know, in order to even write down the equations, I mean, he had to develop all this kind of mathematics. So let me sort of just, you know, a few other things. I mean, there's important work on Bose-Einstein condensates. I put this here because it sort of has one additional twist. I mean, you know, it's not only the conserved quantities, but also the broken symmetries which have to be taken into account. But this is a topic which I will not sort of touch at all. Of course, everybody knows that when you look at charged fluids, I mean, then you have to change the standard fluid dynamics, and you go over to magneto-hydrodynamics. You can do relativistic hydrodynamics, which is very important in astrophysical applications, and many, many, many more. Now, today, sort of the talk is about, you know, not such a huge field. I mean, when you look at fluid dynamics and other things which I listed, I mean, thousands of people are working in these areas. But so it's a small thing, but it has been very active in condensed matter physics. And the reason why I like it so much is that it sort of has a new twist, and I'm going to explain to you, which is not present in all the other items which I mentioned. Now, the other thing which I should sort of emphasize is that, I mean, Euler, you know, and his contemporaries, they were in the lucky situation that they could easily sort of do experiments with fluids, and, you know, they sort of more or less guessed the fluid dynamical equations without actually knowing, you know, how matter was made up. I mean, they didn't have, well, certainly they didn't know about atoms, and then, but they didn't have to decide. I mean, they were sort of, you know, guess more or less the correct hydrodynamic equations directly. Now, in all the other items which I listed here, this is no longer the case. I mean, you see, if you want to do, we cannot do experiments with super dense neutron stars. I mean, that's just sort of out of scope. And the same is true for all these other items. I mean, and therefore, in order to actually really write down the hydrodynamics, you need an underlying microscopic theory. Okay, and so you know, you cannot guess like Euler. I mean, you have to sort of start from a microscopic theory and then make good arguments in order to figure out what would be the correct hydrodynamic description. But once you found it, of course, hydrodynamics is sort of, you know, a marvelous theory with lots of physically interesting predictions. So here I will be, you know, sort of slightly unspecific at the moment, but what you should think of is that sort of the underlying system I'm thinking of our field theories, either classical or quantum many particle systems. So I will be a little bit more specific, but that's the kind of things which are sort of have in mind. Now, there are two important sort of foundations for hydrodynamics. One of them is the local conservation laws. I mean, I noticed that, you know, the word local will sort of reappear at every slide almost, but I think if there's one thing which you sort of, you know, are left with after the talk, I mean, then you should remember how important this notion of local is in order to sort of use the methods of hydrodynamics. And the second thing will be the propagation of local equilibrium, which I put the equilibrium in quotation mark because, you know, what is actually exactly propagating, we have to think. And of course, you know, for fluid dynamics, I mean, it is indeed, you know, what everybody understands by equilibrium. But once you come to generalized hydrodynamics, I mean, you know, the notion of equilibrium has to be changed a little bit. And you will see, I mean, so that will be one of the points, I mean, which I'm going to make. I mean, what is really sort of the correct notion of propagation once you go away from the standard cases. Okay, so I agreed with Abhishek that, you know, if you want to ask questions, I mean, I know it's always sort of a little bit impersonal and it's a large audience, and but you know, if you want to ask questions, I mean, you know, I'm happy to try to answer. Okay, so let's see. So I start with a reminder, which of course you know, everybody knows, but I think it's
maybe I can interrupt.
Excuse me.
Can I interrupt? So
Yes,
you said
Deepak, yes.
You said propagation of local equilibrium, but is it actually propagating or re-establishing local equilibrium at every instant of time?
Okay. All right. I mean, yeah. No. Of course, you're right. I mean, so I will come to. You will understand why I put the quotation mark a little bit later on. I mean, it's too early, so to speak, to really discuss exactly what I mean by local equilibrium.
Okay.
All right. So let me just do a reminder, and because you know, eventually we were going to study systems in one dimension. I mean, the reminder. I mean, just to keep things sort of, you know, short, it is simply a one-dimensional fluid. I mean, so I put here particles on a ring. I mean, I have periodic boundary conditions. I put here, I mean, you know, it has length L, I mean, or volume L. I mean, I put here confining. I mean, you know, we're doing hydrodynamics. It's far away from anything like a scattering situation. I mean, it must be a mechanism which confines the system, and there are various ways to do that. You know, there are walls, and anyway. So for me, I mean, putting it on a ring is sort of very convenient. And of course, I'm thinking of identical particles. There's no disorder in the system. I mean, you know, all the particles sort of interact in the same way, and that's the kind of system which I want to look at. And so, you know, I'm looking at a specific case of a one-dimensional simple fluid. And so I have particles with position and momentum, which are labeled from 1 up to n. And of course, everybody knows that we have the conservation laws. I mean, so there's the number n, of course, which is trivially conserved. But since I put it on the ring, also, if I look at the total momentum, this will not change in time. If I look at the total energy, which is sort of, you know, the Hamiltonian, I mean, the thing which actually also governs the time evolution, this will also not change in time. And it has two parts. It has the kinetic energy, and it has here sort of short range interaction potential. I put here an F as a subscript in order to distinguish from another potential which is going to come up later. Okay, now the point is that you know, these things are not changing in time, but they have a second very important property, namely they have densities which are local. And just to make sure that everybody understands, I'm writing down the densities for this particular case. I mean, just, you know, so that this basic notion is clear. So for instance, if I look at the particle number then the corresponding density is just sort of a delta peak at every location at the positions of the particles. And of course, if I start integrating this over x, I mean, which is my coordinate in the volume, then I will get simply the number of particles. You can do the same thing for the momentum. I mean, then you know, you have to multiply this with the momentum of the chased particle. When I look at the energy, it looks already sort of slightly more complicated. I mean, of course, you have the kinetic energy of that particular particle, but you also have the interaction potential of that particular particle, you know, over which I do the sum Qj, interacting with other particles. I mean, so this is the Qi. And if the potential which I put here is reasonably short range, then you see that the density, of course, is not strictly local. I mean, this one is a strictly local density. It's really exact at the location x. I mean, this has sort of a little bit of extent because, you know, the potential is not a delta potential. It sort of has some spread over which you can see the interaction. Okay. Now, once you have such kind of local densities, then you can ask yourself what is happening to, you know, any one of these quantities when I integrate them over one particular volume element. I mean, so this is, let's say, it has nothing to do with, it has nothing to do with the length L over here. It's just sort of one given volume. And then because of the local conservation law, if I want to change, if I wanted, for instance, look at how the energy is changing in this little volume, then, you know, by these local conservation laws, I mean, you know that it's changing only through the boundary, which in one dimension is particularly simple. It's just the right and left-hand border of that interval. Okay, so now you can do a formulation sort of in the continuum language. You write down the conservation law as a continuity equation, and which has sort of the familiar form. In our case, we have 3 conserved quantities, and therefore we have sort of 3 conservation laws of that particular type. Now, I emphasize that x and t, space-time, are parameters in this equation. And rho m is really still a complicated object. It's a function on phase space. I mean, the function of phase space, which I have written, or if this would be quantum mechanics, then this would be an underlying field operator. So, of course, you know, this is an identity, but it's sort of an identity for rather complicated objects. Okay, so that's fine. So now let me sort of come to the notion of local.
Herbert, I have a question. Herbert. Hi. What happens if you have a system which is integrable? Means it has.
So that's going to come. That's going to come. Yes.
Okay.
That will be the topic of my talk. But what happens if the system is integrable? Yeah. So okay. So you just be a little bit patient and
okay. All right. Okay.
All right, now let's come to local equilibrium. Now, of course, in the long time limit for the system we are considering, I mean, sort of, Boltzmann proposed that the correct prescription of the long time limit would be the microcanonical ensemble. But then, you know, sort of he and of course Gibbs realized that it's actually slightly more convenient, and for us it will be sort of very useful to work with the Gibbs ensemble, which, of course, you know, for very large system size, and if I look at local observables, you know, I mean, the kind of expectations which I'm computing will be identical. I mean, it's sort of, you know, smaller order corrections when you take a large system size. But the main point about the Gibbs ensemble is when you write down the formula, then you see what you have to do. I mean, of course, you're used to putting here the total energy always, and then also the chemical potential for the number of particles, but you should also include, when you do hydrodynamics, you should also include the mean velocity. Usually it's such a trivial factor that, you know, we forget about it. But the point is that what we do, the prescription which we learned from Boltzmann and Gibbs, is to put a linear combination of the locally conserved quantities up in the exponential, okay? Now, you know, these prefactors then have sort of historical names, and of course they are of physical importance. But the main message is that if we would have, and that's already a little bit, you know, part of the answer to your question, if we have a system which has more conservation laws than the three which I listed, then, you know, we just follow Gibbs and put them up there in the exponential. Now, what is the idea of hydrodynamics? It's very, very easy. I mean, so when you look at space-time, I look sort of a little volume element. And then the claim is that sort of, even if I weigh out the system by its own sort of typically rather chaotic dynamics, we'll manage to have one particular local Gibbs ensemble in this sort of little space-time region, which of course is then characterized by these parameters. And these parameters are slowly varying throughout the system. Or you can also put at initial time, you can assume that your initial state is constructed in such a way that it's not a uniform equilibrium ensemble, but an ensemble where these parameters beta, mu, and n are slowly varying throughout the system. And then the assertion is that at least in approximation, this kind of situation will propagate in time. So now we have no equation yet. I mean, we're just sort of asserting that there's a particularly sort of statistical property which sort of is maintained in time. At least if we're not well, it's sort of pretty much maintained in time. But now, of course, once we know this, I mean, we can actually figure out what would be the equation which governs, the local evolution of these parameters. And to do that, I mean, all what I have to do is I have to sort of average my original conservation law. Maybe I can do that here. No, I mean, maybe let's see. Okay, anyway, so I'm afraid to go back. I can do it. Okay, so you can average this conservation law, which of course you can average over everything. But now the claim is that we average this over a particular kind of average, namely in a local Gibbs ensemble. So the bars are now average quantities and they depend only on XFT. So these are really functions on space-time. And once you do this, I mean, you get a coupled system of conservation laws, which are your hydrodynamic equations. But the main point is that from this Gibbs, local Gibbs construction, you can actually express these average currents as functions of the equilibrium parameters. And so it's that step which makes first the evolution approximate, but secondly, gives you a closed system of equations, which are the hydrodynamic equations. Okay, so I want to advertise one. I see. I have to sort of watch out for time here. Okay, so I have to advertise one small a very nice simulation of Abhishek. I mean, who sort of simulated these things in one dimension, so this is sort of blast waves. I mean, so this goes back to the Manhattan project. But the reason why I recommend to look at this, you see, once you do a simulation, I mean, there are no free parameters at all. And it's still, despite the fact that I have seen many pictures of this type, it's still amazing to see how particles do follow, this hydrodynamic equation. Okay, so now the next question which I want to address here is the question, are there more conservation laws? Okay, so you see, if there would be more conservation laws, I mean, you better have to include them, because otherwise the system will not become closed. And so the belief is that generically, it's just the three of these conserved quantities, but maybe we were not clever enough. Maybe there are some other conserved quantities. And of course, yes, I mean, it depends a little bit on what kind of interaction potential we choose. If I decide to just take an ideal gas where this VF is equal to 0, then of course, we have an infinite chain of conserved quantities. If just take, instead of the first and second, I take just higher powers of the PJ, then these will be always conserved quantities. And I use a notation for them. I put here an M which sort of labels in this particular way, the conserved quantities. But there are more complicated systems. I mean, if the system is integrable, I mean, so for instance, if you look at a collateral system, then you will see that for that very particular potential, the 1 over sinh x squared potential, you have also again an infinite list of conserved quantities. So we say generic no, but we have counterexamples. But the surprising thing is that when you look up the literature, then it seems to be an empirical fact that it's either 3 or infinity. There's nothing like 57 system with 57 conservation laws. Okay. Now, the generalized hydrodynamics, which I will tell you a little bit more in detail, actually is a particular case like the collateral case, where you have an extensive number of local conservation laws. So, in the large n limit, I mean, it will be sort of an infinite number of local conservation laws. Now, one thing which we now know already very easily is that, rather than taking local equilibrium, which is linked to the fact that we have only 3 conservation laws, you better generalize your notion of Gibbs ensembles And you have to, this was the Gibbs prescription, you have to put all these conserved quantities in your exponents. So now the GGE, as people say, has a more complicated form and has an infinite number of chemical potentials. And the QM, I mean, they have to come from analyzing whatever particular model is. I mean, so, you know, if you do the Kalotscherer, it will be some particular form, and for others, some. But this is a purely static notion. So equilibrium has to be generalized to the generalized Gibbs ensemble, which depends on sort of an infinite set of chemical potentials. Okay, but are there more conservation laws? Well, that's I mean, was for a long time a completely open question. I want to, despite the fact that I'm running a little bit short, I still want to share with you a really interesting result by Shiraishi in Japan, and he has the following result. I mean, so he looks at the spin 1/2 XXC chain, which is of the usual form. I mean, you assume that the couplings between, these are probably spin 1/2 matrices. You assume that these couplings are all non-zero, and you put an external field H. Okay, so your Hamiltonian is local. I mean, this is just sort of nearest neighbor coupling, so you have a local density. And if you want to do if you ask yourself what would be a local conservation law, then you do exactly the same construction. You take some general observable, which is sort of here labeled by the lattice side, but it's supported not maybe in a block of 2, but maybe on a block of length kappa, where kappa is arbitrary. So here I put sort of an example of such a potential local conservation law. It's just 3 sides. There's the one inside, and then there's a left border, and there's a right border. Okay. But now, of course, if I have, the block length kappa, I mean, there will be 4 to the kappa potential local observables. Well, the condition which I have to put on the QJ is that if I work out the commutators, so to speak, the time evolution of this Q, I mean, then it must be of conservation type. So if you work out this commutator, the condition which I have to impose on this density is that it must be of difference form. I mean, so, Ij is the current going in, and Ij plus 1 is the current going out. So it must be of this particular difference form, where it's just like in this notation here, the Ij plus 1 is simply the same operator, the same function shifted by 1 unit. Okay? So, it's just a complicated, huge set of in a linear space, and then which is sort of constrained to satisfy that particular condition of local conservation. And the result of, so we know that if I take the external field to be 0, then that's the XYZ system. I mean, that happens to be integrable. And we also know that if I take the X and Y coupling, X and Z coupling, the X and Y coupling to be equal, that's the XXZ system is also integrable. So there we know that we have an infinite collection of conservation laws. But the result of Shiraishi is saying that if I exclude the 2 cases where the system is integrable, then the only one which is locally conserved is actually the energy. And that, I think, is a very remarkable result, because it tells you that, this naive intuition, if I put some interaction, it will be certainly not integrable. I mean, this can be, in this particular case, can be actually confirmed. Okay. So, of course, the result is expected at much, much greater generality. But sorry for doing this again, but I mean, let me just again say how important the locality is. You see, if I take just my Hn in a finite ring, I mean, the one which I had before, the XYZ model, then, of course, any operator which is diagonal in the energy basis will be time invariant. Okay. But it certainly will not have a local density. It's a fact that there's a local density which sort of cuts you down just to a single observable which satisfies the condition. Now, as I said, integrability is very, very easy to break, and the result is expected at much, much greater generality. But it's a recent result, and I hope in the future maybe there are more things to come which sort of can verify this for a larger set of systems. Now, let me just say that having this information gives you already sort of can sort of translate into what you should see physically. So if I take the non-integrable case, and Shiraishi tells me that there is no other conserved quantity than the energy, then there will be just a single carbon. I can, in this case, the Gibbs state just has one single parameter, which is the inverse temperature, which is the beta, the inverse temperature, and you can compute the carbon in this Gibbs ensemble, and you find that there's 0 carbon. So then you know, all the sort of fun terms, I mean, the whole Euler terms sort of vanish completely, and presumably, you know, you have to go to the next order correction, which is the Navier-Stokes, and presumably, you know, all what will be happening, and that's sort of, you know, confirmed for many systems, is that you just have diffusive broadening. So if I imagine to start with a completely homogeneous state, sort of infinitely extended, I put a little bit of perturbation at the origin. All what you're going to see is sort of a diffusive peak, which is standing still, and which has a square root of t sort of spreading. So this is, of course, you know, there are more details to be done, but once I know that the energy is the only locally conserved quantity, it's sort of some sense of rather natural sort of consequence. However, if I'm in the integrable case where I have sort of now an infinite number of conserved quantities, then of course, you know, I have lots of carbons which have non-zero averages. There will be sort of, you know, a dominant ballistic contribution. And in this simple experiment, which I'm proposing, just sort of, you know, put some perturbation at the origin, you will see a totally different picture. Rather than having the square root of t spreading, now you have a ballistic spreading. So this is proportional to t. And there will be some scaling function which tells you what this peak is, the shape of that peak. And of course, you know, there's the 1 over t in order to satisfy the conservation law. So it's spreading, and at the same time, these peaks are decreasing, like 1 over t. Okay, so so now I'm sort of coming to the actual sort of center of the talk. Namely, the question is what is actually happening if I'm in the situation where actually the system is integrable. So this is what in the literature is called generalized hydrodynamics. And the corresponding local equilibrium I mentioned already is named generalized Gibbs ensemble. Okay. Now there are 2 important papers in this area. Here there's sort of a list of possible candidates, which people have investigated. Of course, there are more models which are integrable, but it's always sort of fairly specific models. But there are two surprises which sort of were somehow not really expected. And the first surprise is that on the hydrodynamic level, all integrable systems are alike. Now, how alike, I hope I have the time to tell you, but of course, you know, these systems are very different. I mean, you know, classical Toda lattice and the Fermi-Hubbard 1/2 is sort of a very different system. Nevertheless, once you go to the large-scale structure, the hydrodynamic scale, I mean, then you will find that, you know, they sort of share a common structure, which I hope I can explain to you. And the second surprise is that the GGE average carbons are actually computable. I mean, that's sort of somehow, you know, the basis of these papers. Now, why should you be surprised? Well, you see, when you look at the conserved fields, I mean, like energy, momentum, and then maybe higher orders conserved quantities, which come into play, then you know, once you know the free energy, it's just a derivative of free energy. I mean, so once you know how to compute, you know, sort of this generalized free energy, you're in good shape. And if you know, part of you studying this integrable systems, I mean, mostly you have some information about the free energy, right? So the fact that you can actually compute averages of the conserved fields are not really surprising. But when you look at the average carbons, they are no longer derivatives of the free energy. I mean, you can look at formulas, you know, there are expectations. I mean, you know, if you can write down what is the microscopic expression for the carbon, but these are complicated functions and operators, and doing their GG average sort of looks like completely impossible almost. Nevertheless, it can be done. And you know, this is actually a subject which I like to talk about, but I will not go into further details because, you know, things have developed since 2016, and now we have a much better understanding what's actually going on. But let me not do this, okay? So then what can I try to tell you? Well, I mean, what I really would like to tell you is, you know, what does the hydrodynamic equation look like in the case of an integrable system? But this is not a two-liner. So, you know, I cannot, of course, I can just write down the equation, but it would be pretty meaningless. And therefore, what I want to do is I want to sort of give you some explanations and some intuition what's actually going on in the simplest possible systems. Now, of course, I cannot make it too simple because, you know, I mean, you would not be so much surprised if I tell you something about the ideal gas. I mean, this is not really such an interesting system for that purpose. So I picked the one which I understand best and which I think still is sort of the one which is sort of best understood. And so I will give you some explanations for the classical Toda lattice so that I can sort of, you know, fill in this word sort of slightly more concretely. And then at the end, I do some hand waving. I write down for you the hydrodynamic equation, but it's more the hand waving before you should watch rather than the hand waving when I'm going to write down the hydrodynamic equation. Okay, so let's have a look at the Toda lattice. Okay. So this is now classical. So we are just realm of you know, many interacting classical particles. We are in one dimension, as I discussed before. But now, rather having sort of a general fluid potential, I take a very special one, namely just this exponential function, and it depends on the nearest neighbors. Okay. So this is the famous Toda lattice. Was discovered in Toda. He was sort of looking at nonlinear wave equations and tried to sort of look at their discrete version. The system has no free parameters. If you sort of you know, put here parameters or some strengths and also here some decay constant, they can all be scaled out. I mean, so it's a model with no free parameter whatsoever. Okay. Now I have to put boundary conditions, and for the momenta it's the obvious boundary conditions. For the positions, I sort of repeat the configuration up to a shift by L. I mean, so here's, let's say, my initial configuration in a box of size L, and then I just repeat it. Okay. This might look a little bit strange to you, but I have to remind you that we want to confine the system. It should be, you know, a thermodynamic system, and of course there are various ways to do that. Of course, I can just put my box as you learn, but this is not such a good idea. Then you might break integrability, and as I told you, you know, it's a very fragile property, and then if I just put naively my finite volume, my confining mechanism, then you're in trouble. So, but this is a good way to do it. Okay, so how to find the conservation laws? Now, these are two papers by Henon and Flaschka many years back, and Henon sort of he just played with the formulas for small systems, and then he had an ingenious idea to understand what the conserved quantities are for an arbitrary number of particles. But Flaschka had sort of he's from the Courant Institute. I mean, he had sort of a somewhat different vision, and what he observed is that you introduce sort of, which everybody actually did in this area anyhow, you introduce new variables, which is simply the square root of this potential. Now, you could take the potential itself, but it's the square root, which is sort of a little bit more easy, and then you can write down the equations in these new variables. And now it looks sort of very algebraic. You see, I mean, it's just sort of here a quadratic term, and then here another quadratic term, and of course you have to shift. And anyway, so this is what they look like. And in this language, the periodic boundary conditions are the obvious one. I mean, you just sort of do the boundary condition in the A variables, which is this one, and in the momentum variables, which is the one over here, right? I mean, so now you have a new phase space. You have a new Poisson bracket. I'm not going into this at all. I mean, just say that, you know, take this as convenient variables, which sort of allows you to do some analysis. Now, why is this sort of, you know, such an amazing new basis? I mean, we could have thought maybe about others. Now, but what Flaschka observed is that you can rewrite your equations of motion in a matrix form. And here it goes. I mean, so you take your dynamical variables and you range them in an n by n matrix. On the diagonal, you put n momenta, and on the off diagonal, the first two off diagonal, you want to make it symmetric. On the first off diagonal, you put the a's. I mean, that's the square root of the potential. But you see, there's still one missing, and because of the periodic boundary conditions, you make the obvious choice. I mean, you put the a n here sort of up in the corner. So it's a triangle matrix. And you divide this sort of, it's a pair. So you know the other part of the pair is usually, I mean, this is called Black's matrix, and this one is the pair, which has no specific name. And you basically construct out of this sort of a skew symmetric version. I mean, so you put here a and minus a, and a and minus a n, and then of course the diagonal has to be zero. And then, you know, it's a simple thing, but once you had the idea, it's a simple thing to check. Oops, this is not what I wanted to do. No, sorry. Okay, it's a simple thing to check that this matrix, now the Lax matrix evolves according to the equations of motion and satisfies the simple matrix equation. And when you stare at this, you see that this one is Q-symmetric, so it generates a unitary. And so this means that the spectrum of Ln at time t is the same as the spectrum of L at time 0. So when I write down the eigenvalues of this matrix, which is here the standard eigenvalue equations, of course, are real, then you discover that the eigenvalues are conserved. And there are exactly n of them. So hooray, we are done, and we found all the conserved quantities for the finite system of particles. Okay, but I mean, Henon wrote down something a little bit related to this, and of course he observed, and we conserved, everybody observed immediately that these things are not local. You see, they are conserved. I mean, that's fine. They do exactly what you're supposed to do, but they are not local. And so in some sense, you might think that these are sort of useful things. I mean, you know, these are things which would have been ruled out by the Shiraishi result because they are simply not local. They don't have a local density. But now, I mean, this is also what Flaschka observed. I mean, there's a very simple way to actually make them local. And the idea is that you simply take powers of the Lax matrix. So I take the mth power of the Lax matrix and take the trace of that. That's some function, complicated function on phase space. But, you know, I can work out the trace. That's just the sum of all diagonal elements. And now you see that this is, of course, a density. But the question is it local? Well, you know, this is a tridiagonal matrix. And if you just work out the matrix, work out the matrix product, then you can convince yourself that that's indeed local. And here I sort of make sure that you understand this. I mean, so, you know, it's sort of like a random walk type of thing. It's a tridiagonal matrix. So you do a walk either going up, staying constant, or going down. And in the case of m equals to 6, I mean, you have to take 6 steps. I mean, so, you know, when you do this particular function, it's the sum over all random walks going from j to j. So here I have 0 to 0. I mean, and going up and down according to the rules. I mean, of course, there are you know, 3 to the 6 such walks. So, you know, it's a complicated function, but it's nevertheless still a polynomial of order 6. And the way how it works is that this one is sort of the A0, but this one has to go down again here. So this gives you the A0 squared. Then this you know, the diagonal terms are the P. So this is the P1, so you get the P1 squared, and this gives you the A1 squared. And so you should think of this some complicated polynomial, but nevertheless, I mean, you have an explicit formula for the densities. Okay, so now we are done. We know that this system has exactly sort of n conservation laws. And what I said about the carbons, you can also see that if you want to compute carbon averages, it really requires eigenvectors, and the eigenvectors is a more difficult information than simply the eigenvalues. Okay, so now let's see how we can continue. Okay, so now I constructed the conserved quantities. So what is the next item on the step? Well, the next item is we have to construct what is the generalized Gibbs. Okay. Now, I recall that even if you have very many conservation laws, all what I should do is put them up there in the exponentials. So this is what I've done over here. Okay, so, you know, maybe it's just a large finite sum, but anyway, here I put sort of, you know, chemical potentials, which except for 0, 1, 2 have no physical meaning. But if you do hydrodynamics, I mean, you have to keep them. And here is sort of my global conservation law. And of course, m equal 1 is just a diagonal, so that's just the momentum, and m equal to 2 would be the energy. Okay, and now you see that if I make this definition, so it's just a power series for this potential, then you see that the weight which I have to put up here has sort of a nice form. It's just a trace of some given function of the Lax matrix. And this V, I mean, you know, when you look at it, you know, if you want to make this exponential sort of well-defined, I mean, then you know, it should be integrable, or it should have a finite trace. I mean, then you see that what I have to do is I have to make this potential sort of going up. And so this is I like to call this the confining potential. It has nothing to do with the potential we had originally. I mean, it's the confining potential, and it's this confining potential which, so to speak, labels the particular GGE. So one case would be take V equal to the potential, just the harmonic potential, just V squared, and we are back to thermal equilibrium. But now if I add sort of like a quartic term, then we'll have some other one. I mean, then you have the sort of double well structure, or you can take more complicated things, okay? So now we have sort of a convenient label, so the confining potential is independent of the system size. So what we have to do is we have to study such kind of Gibbs factors in the limit of large system, okay? But now comes sort of an important insight from looking, you know, at the legs and this kind of generalized Gibbs. You see, this gives you, this object tells you that we actually have a random matrix, right? I mean, so if I go back here, you see now all these matrix elements are actually random because they are distributed according to the Gibbs, the generalized Gibbs. Now, what is special about thermal equilibrium? Well, you know, it's trace squared, and so there you see that the entries are simply independent. So for the thermal case, these entries are here the simple Gaussian, and here they are what people call the chi distribution. So there is a triangle matrix with independent entries. But if you go to the full GGE, I mean, you know, all these matrix elements are correlated in a complicated way. But, you know, there is a prescribed formulas. And you can sort of convince yourself that, you know, when I look at these kind of generalized Gibbs ensembles, these are complicated functions, but they have the property that all their correlations are actually decaying exponentially. I mean, so you know, there's no phase transition in such systems. Okay. So now we have sort of a different point of view. You see, a different point of view of the conserved quantities. I mean, let's go back to you know, these particles evolving in time. Now, then you look at the small portion of your system. Well, I mean, you know, you see just these particles moving, and then maybe they're a little bit denser, and otherwise they're, you know, they're just sort of moving and making their sort of softened collisions. But you will see nothing sort of which has a slow variation. You know, it's invisible to your eye. But now we have sort of we realize that what is actually invariant, which is actually slowly changing, are actually not the eigenvalues, but the sort of, you know, the trace L to the M. Now let's just rewrite this in a slightly more convenient way. So I take this Lax matrix, which is random, and I define the density of states, and which is the standard notion. I just put a little delta at every location of the eigenvalue, and then I normalize this to 1 by dividing this by 1 over n. And now you look at your formulas for the average value of the conserved quantities. Well, that's just the average values of the summation over the lambda here. Maybe I should go back to this thing. You see, it's the average of this quantity. But this average is nothing else but the moments of the density of states. And so rather than thinking of these moments, it's just much better to think directly of the density of states directly. And it's that quantity which has a slow variation. It's that quantity which has a well-defined, you know, non-random limit, which is called rho p, which of course depends on the particular confining potential. But it's that function which sort of characterizes in a very direct way what is your generalized Gibbs ensemble. The V is sort of, you know, sort of slightly indirect. It's a parameter in the Gibbs state, but it's this quantity which is sort of related to the objects which I would see. So what is the prescription now? If you imagine now that you have a time-dependent situation, and what you're supposed to do if you want to do hydrodynamics, of course, you still look at this sort of reasonably small space-time region, should have sort of a sufficiently number of particles, maybe, I don't know, maybe 10,000 or so. But now what you're supposed to do is you're sort of are supposed to form the Lax matrix out of this data. So you have the data, the Q's and the P's at time t. You form out of this the Lax matrix, and from the Lax matrix you form the density of state. And it's this density of state which is going to vary slowly. And it's this density of states which will satisfy the hydrodynamic equation. Okay, and this is sort of a rather surprising structure that, you know, out of this sort of somewhat diffuse, and you have all this complicated sort of polynomial, there is sort of a rather sort of simple quantity, which simply are, you know, the density of states of a particular matrix, which some correlated, maybe complicated correlated matrix elements, but nevertheless with a well-defined density of states. Okay, so now I made this a little bit long, but let me sort of just go to the thing, you know, I wanted to say how to compute. I mean, so let me just sort of, I mean, throw some formulas at you, which of course now they are sort of not too much motivated anymore, but still, you know, I promised to write down the hydrodynamic equation for you, so you have to suffer for another 5 minutes in order to sort of see what I do here. So the first thing is that there's something which is called the thermodynamic beta ansatz. Now for the Toda lattice, there's no beta ansatz whatsoever, but nevertheless, that's sort of, you know, this similarity between different systems. There is an equation which comes up, which actually in all the cases turns out to be sort of, you know, the Euler-Lagrange equation of a particular variational problem. I mean, to every one of these integrable systems, we have a variational problem. And if you write down the Euler-Lagrange equation for a quantity which people call the quasi-energy, then you get this kind of equation, okay? So this is the quasi-energy and satisfies this nonlinear equation. Here you see the confining potential, which appears explicitly, that labels your particle GGE. And here you have another quantity which sort of comes up very surprisingly, namely you see the two particles scattering shift of the Toda lattice. Okay, so I have no time to really explain this in more detail, but this function is actually model dependent. So if I take the delta Bose gas, then you will see here the Lorentz function, Lorentzian, sitting in your kernel. If you do some other one, it will be some other function, but it will be always this dynamical function which you can compute by just looking at the motion of two particles. And then I have here the e to the minus epsilon of w prime. And so here from this, from the confining potential, which are sort of your chemical potential, you can compute the quasi-energies, and from the quasi-energies you can compute something which is called the number density, and from this you can compute two other functions which are called particle density and this number density, and they are related to something which is called the dressing of the constant function. And here I've written down for you this particular dressing information, so dressing transformation. It's just sort of a linear transformation on functions with the kernel which is related here, which the kernel which is given by the two particle scattering shift. The other thing which I should mention is that even the quantum mechanical models sort of have a similar TBA equation, rather than having the exponential. I mean, now you have to put in, if you have fermionic excitations, you should put sort of what you know from independent fermions. It's a log of 1 plus e to the minus epsilon, right? I mean, so this equation is very universal, and we know how to modify it for various classes of systems, and we always have here the two particle scattering shift. Okay. Now this is not yet the hydrodynamic equation. We have done sort of just average values of the conserved quantities, but you can do something similar for the currents. And again, I have to throw at you just a formula, namely what is called the effective currents can be computed through this formalism. So it's just sort of the dressing of the linear function divided by the dressing of the constant function. I don't want to go into further. I mean, it's you know, you will not be able to understand unless you have really some background. But I want to write for you now the hydrodynamic equation, and just assure you that, you know, for this density, local density of states, it has sort of the standard form. I mean, you see, this is the space-time x, the space-time point xt, but now at every point, I mean, you have a function which is the density of state, and the density of state is evolving according to a conservation law with a very complicated nonlinearity, which is sort of, I tried to indicate in the transparency before, but it's a very concrete and explicit formula, and you know, you can devise methods to produce numerical solutions. I mean, you can look at special solutions and all kinds of things. So this is sort of goes into more details than I can do, but at the very end, I want to convince you that you know, this is not only pure theory, but there's actually an experiment. There are more experiments by now, but there's one beautiful experiment which fits nice into this structure by Bouchol and company. And you see, I mean, of course, you know, at the ICTS, I mean, people knew about this development, and we had a very good workshop in 2019. I invite you to actually look at the lecture of Jérôme Dubail. I mean, he actually explains you much more about this experiment than I can do here. But all what I want to say is that it's called Generalized Hydrodynamics on an atom chip. What you have is sort of a chip, and you, by some magic, which I don't really understand, is you can build something like a magnetic tube, which is sort of, you know, very narrow and extended, and you can fill it with rubidium atoms, which we know is sort of you know, extremely well modeled by a system of quantum particles interacting through a repulsive delta potential. So that's the famous Lieb-Liniger delta Bose gas, and that's a very sort of good experimental realization. What they do is they start with some sort of, you know, initial density, which for instance, you can take such a double hump, and then they let you know, the gas sort of expand into this narrow tube. And what they can measure is sort of the density at time t. Well, you measure the density at time t, so you can compare this directly with the hydrodynamic equation. And the first thing which you might want to do is just do conventional hydrodynamics, just 3 conserved quantities, just like what we had in the beginning. I mean, you know, just number, momentum, density. And then when you look at it, it's a very poor fit. Actually, you know, poor is sort of a friendly word. It just doesn't fit at all. And the reason is that when you look for such kind of initial data, you know, the system will develop shocks, and you know, in these experiments you simply don't see any shocks. I mean, so it will not do very well. But you will find a very good fit, and that's what is you know, fit with generalized hydrodynamics, fits very well. But you know, as a message, once you do theories, it's a different ballgame from when you do experiments. So you look at this experiment, everything looks fine. I mean, you know, you believe me. I mean, you can look up, you can listen to Jérôme. Life looks perfect, and you say, ah, you're way, you know, I found sort of a nice experiment. But then, you know, when you talk to the people more closely about this experiment, they tell you, well, look, I mean, I can count the particles, you know, at the final time, and what I discover, rather than having 4,000 particles initially, there are only like, you know, 3,200 left, not all the 4,000. So our beautiful conservation law of the number of particles is actually not, is simply doesn't hold in that experimental realization. Okay, so you can do 2 things. I mean, you can either try to think about another experiment, or maybe try to make this even better. I mean, but you know, that's easily said. It's not such an easy task. Or you can say, well, you know, that's true, but you know, these particles are evaporating slowly. So you have to add to your hydrodynamic equation sort of a loss term, which takes this non-conservation law into account. Now, this is something you can do with the computer and piece of papers. And in fact, Benjamin Doyon and then Jeremy, I mean, they worked out the theory. And if you do this, I mean, you find an even better sort of agreement with generalized hydrodynamics. So I think this is sort of, well, my time is up, but let me just put anyway, still all my best wishes for joyful holiday seasons, for a successful year 2001, and for a happy Foundation Day. So thank you very much for your patience.
Thanks a lot, Herbert, for this really great talk. So, so people can ask questions now. Vijay, yeah.
Yeah, can I? Yeah. Hi, Herbert. Thanks. Very nice talk. So I wanted to understand this. When you do classical hydrodynamics of liquids and liquid crystals, one typically starts by writing down conservation laws, the densities of conservation laws, and then does write down the equation for the entropy production rate. And then you do Onsager-like pictures of forces and fluxes. And so how does that connect with this generalized thing? I missed that. Is it because there's an infinite number of conserved quantities that doesn't come here?
Well, I don't know. I mean, if you do liquid crystals, I mean, don't you have to do also the? I mean, you have broken symmetries, right?
That's correct.
Yeah. So this is what I tried to mention. I mean, so there's another, of course, highly interesting area of hydrodynamics where you actually have to take into account also, you know, I mean, yeah, you have to, you know, your order parameter, you have to take into account the broken symmetries. Now here in this system, it's one dimension. I mean, there we know that you can also break, I mean, you can have phase transitions also in one dimension, but you need, you know, potential which has a decay like 1 over distance squared, right? I mean, that's sort of the famous Dyson result and work afterwards. And here in our case, by all what we know is that these generalized Gibbs states, I mean, they all have exponential decay. So we are actually in a region where we have many conservation laws, but no broken symmetries.
No, but even if a simple fluid, no, let's say not a liquid crystal, but just one which doesn't have any order parameter sitting there, but even there, one writes down the usual entropy production rate and identifies forces fluxes. That's the, so okay. I didn't the connection between these two pictures.
Okay. Okay, but you see, if you want to do entropy production, I mean, you know, you better have to take the dissipative terms into account, right?
Yeah. You
know, I mean, the entropy reduction is something which comes from, I mean, of course, you know, there's this subtle phenomena that the entropy production can come from sort of, you know, somewhat sort of singular solutions of the Euler equation. But the generic way how you have entropy production is to have dissipative terms, right?
Correct.
Okay, so the question is, where are the dissipative terms? You are totally correct. I mean, of course, this equation is just the analog of the Euler equation. You see, there's just a first order derivative. It's just hyperbolic conservation law. There's no entropy production whatsoever. It's you know, and of course you can sort of write down what the entropy is for these systems. You can work it out, and you confirm that there's no entropy production at all. Now, that's not the end of the story. I mean, what people realized, I mean, these are all results sort of, you know, which appeared, I think, more or less, you know, during that year. I mean, so you can ask yourself, you know, is there sort of like a second order dissipative correction to that equation? And the answer is yes. I mean, so people can write down the Onsager, they can write down the sort of the Onsager matrix. I mean, you know, it's of course will be now an infinite dimensional matrix.
Right.
But you will still have the same structure. It will have second derivatives with respect to x, right? I mean, that's a dissipation, but then instead of having a 3 by 3, or depending on your system, sort of a matrix, a small matrix, I mean, here you will get sort of, you know, infinitely many, but you can actually really work out, you can actually, which is very surprising, you can actually work out an explicit formula for your Onsager matrix. I mean, explicit in terms of, you know, these row P's and such kind of quantities. I mean, then, I mean, this by itself might be a complicated expression, but you know, you have to need a computer and actually get a real number. But the point is, there's a very explicit formula, you know, not just time integral over your carbon-carbon correlations, but you can actually work out that time integral explicitly, find the explicit formula, right? I mean, so I think, you know, if you, so I think your question was the point that you know, there's really a correction term, right? I mean, so we are in the situation, there's no symmetry breaking because it's all short range, but definitely there is a diffusive correction, which actually was a big surprise, because, you know, sort of integrability and dissipation sort of seems to be sort of two different things, right? But it's not the case. I mean, when you look at your Onsager matrix, of course, there is sort of what people call the Toda weight, which comes from the fact that you have all sort of this non-zero currents, but then there's still, you know, once you subtract this Toda term, I mean, there's still terms left over, which has typically an integrable decay in time, and which gives you sort of, you know, a well-defined dissipative correction.
Mm-hmm.
I'm not sure whether I'm answering your question, but I'm still trying to see what is sort of special about this and compared to what you had in mind.
No, I guess you get, I mean, it was really about the second order corrections and the diffusive things that would come up. Yeah, partly that.
Yeah, Abhishek, can I ask a question?
Yes.
Thanks, Herbert, for a very illuminating talk. I had a somewhat technical question. When you mentioned this connection to random matrix theory, and you introduced this density of states for the random matrix, and all the quantities are expressed in terms of moments of these density of states, and so on. So I'm familiar with the usual random matrix where you have a Hermitian matrix with some potential trace of V of the M. I was just wondering whether here the fact that the lax matrix is tridiagonal and not your most general Hermitian matrix, does that technically change many of the things that the usual techniques that you apply to study the large n limits of these, the usual Hermitian random matrices?
Okay, so that's a good question. I mean, so first of all, I think it's a different. I mean, so when you talk about random matrices, you think about something like GUE or so, right? Is that what have you in mind? Okay. So in that sense, it's very different, because even if I put this V here, you know, that's of the short range character. I mean, the matrix will be, you know, the matrix is always tridiagonal. So we are very far away from the GUE case. Okay. So in that sense, I could say, no connection. But you saw some other thing from the GUE, namely you saw this logarithmic interaction later on. This I haven't really worked out so much, but the point is that eventually that's special for the Toda.
The Toda case, yeah.
So in the Toda case, what happens is that when you work out the density of states, you discover that the formula which I mean, you know, this formula which you find, for instance, you know, some formula of this type is actually related to the small beta limit of the beta ensembles. So when you look at the beta ensembles, but you now go to a sort of more mean field type limit, I mean, limit where the beta is like 1 over n, then you discover that it's that sort of, you know, random matrix type structure which determines the density of states. So I mean, the matrices which I study a priori are not connected to GUE, but the way you should think about it, you see, there's this famous result of Dimitrov and Edelman, which somehow falls into this place. You see, they were asking, can I take, let's say, the standard GUE, and can I isospectrally find a tridiagonal matrix which has exactly the same eigenvalues, right? And what they found was a matrix which is not so unlikely to the matrix which we have over here. You know, when you look at these distributions, I mean, they are sort of pretty close to what you get. I mean, it's not the same, but they are not so far away. I mean, so the Dimitrov-Edelman result about, you know, how you map the GUE matrix to a triangle matrix in such a way that you still have the same eigenvalues actually is used when you go slightly more deeper into the formulas. Yes. So it's something different, but nevertheless, surprisingly, you know, they have some underground connection. Yeah. At first sight, they look really different.
And the technical way in which you then try to compute the moments for these tridiagonal matrices, I mean, of course, I don't want you to explain the whole thing, but it's,
the technical way is you know, I basically write e to the minus. Let's see. The technical way is yeah, I basically writing e to the minus trace of this thing. Okay. And I try to rewrite in the new variables, right? I mean, so this is so yeah, I have to, you know, that's the original volume element which I have when I write down the partition function for the Toda lattice, and I'm rewriting this in terms of the new variables, I mean, then you get a different a priori distribution for the A's and for the P's. And then you get the exponential of some horrible thing. But now I'm using that this exponential can be written, you know, in terms of the eigenfunction. And then you realize that when you stare at the Dmitry-Edelman paper, there are modifications. But I mean, you know, in first approximation, you stare that they tell you how I can transform the volume elements. Okay. Once I know how, so basically what they tell me is you know, even how under the a priori measure, how the eigenvalues are distributed. And then I, of course, now I have a slightly more complicated way, but it's not so bad because now it's the function of the eigenvalues, right? So Dmitry-Edelman tells me how the volume elements is changing, and the weight is already explicitly given in terms of the eigenfunction. It's just V of, you know, it's an obvious thing, right? And so this is how you get then, you know, you get first sort of a formula for the energy, and then you get a variation formula, and then you can sort of build up the whole machinery here.
So all the moments are computable, you said.
Well, I mean, they are computable modulo that you have to compute this density of states, right? I mean, so for this even in the thermal state, only in the thermal state you can find an explicit sort of analytic formula for that one. Otherwise, you know, even if I take a quasi-confining potential, it's already too complicated. I mean, you have to do a numerical simulation. But we have done numerical simulation. You know, these are sort of, you know, reasonable functions. We know how they behave in particular limits. And, you know, this is a usual kind of thing. Yeah.
Okay, thanks very much.
Sorry, for these quasi-energies.
Oh, sorry.
Yeah, sorry, Herbert. For quasi-energies, you wrote down an equation, which you said in quantum mechanics for fermions, it is log of 1 plus e to the power minus e. For bosons, it is...
this slide more or less, or I mean, this is what happens. This is how you have to modify when you take quantum mechanics into account. I mean, with fermionic excitations, right?
For bosonic excitations, it will be log 1 minus.
Yeah, would be the corresponding other thing. Yeah.
Okay, thank you.
But so I mean, just to make clear, I mean, if I take the delta Bose gas, which sort of you would think is a bosonic system, but you know, the excitation when you write down sort of, you know, the Lieb-Linear, I mean, when you write down the beta ansatz, you see that they are sort of, you know, have fermionic structure, right? I mean, so when I write down this equation for the Lieb-Linear model, then what I should do here is the two-body scattering for the Lieb-Linear, which it's a scattering shift, so which happens to be a Lorentzian, and here I put a logarithm, and then you look up the old Young and Young paper. That's exactly the formula which they have. What Young and Young, of course, never looked at. They had never the idea of looking at the general confining potential. I mean, why would they, right? I mean, they write down this exactly. So this is whatever 69 paper. They write down exactly that equation for the delta Bose gas with the log. But the confining potential is simply the quadratic potential. But now,
thank you.
You see, it's general. I mean, it's not only the Lieb-Linear. It's all models which we look at have the same structure.
Okay, thank you.
Some models haven't been worked out. I mean, for instance, you know, I mentioned the Sinch-Gordon. I mean, that would be one case which one can work out sort of. I mean, the 1 over Sinch squared potential. I mean, you know, I would love to sort of work this out more deeply. There are models which haven't simply been studied because they are sort of, you know, maybe of not such major interest. But the belief is that if you would work out the details, it just sort of follows into the box.
Thank you.
Yes, Benjamin.
Yes, hi. Hello, Herbert. Very nice. Hi. Wonderful talk. I have a very sort of a very elementary type of question. That suppose you have an integrable system, the one you wrote down on the first slide. It is written in terms of certain coordinatization of the phase space. Now, suppose I'm able to perform a canonical transformation to action angle variables in which the phase space is a product of tori, which in many cases can be done using the inverse scattering transform. Is it that those are the right coordinates in terms of which one should do the hydrodynamic formulation?
No, that's a very nice, very good question. I mean, let me see. How should I put this? I mean, first of all, you see, okay, for the Toda lattice, I mean, you know, the transformation to action angle variables is very well understood, right? I mean, so let me just think about this particular case. Now, of course, once you do action angle variables, you lose locality. It's no good for, right? Okay, on the other side, so the first answer is no. I mean, you know, I mean, action angle variables, you use the most central element, and of course you have this nice structure, everything, but they are simply not local. I mean, you know, when you cannot work with them. I mean, so you could ask a more concrete question. I mean, you know, can I compute this generalized free energy, which is sort of, you know, just computing a complicated integral in the new variables, in the action angle variables. I just don't know how to do that. On the other side, when you listen to Benjamin Doyon, I mean, he sort of tried to argue that you know, it's an integrable system and the scattering map is presumably rather well behaved. And so what he was trying to exploit is sort of something similar what you sort of mentioned, namely that that you might want to use the asymptotic sort of scattering map, including the scattering shift, and use this sort of like you know, a canonical transformation. And then from this, if you look in his paper, he argues that from this he can actually compute the generalized free energy. So so in that sense, you know, I'm a little bit cautious by you know, putting immediately sort of, you know, you cannot do it. I mean, in terms of computation of the free energy, I think, you know, the way I proceed is sort of fairly straightforward. But of course, I'm using sort of technology which other people have developed. Benjamin is sort of more original. I mean, he really wants to use the scattering map. And but you know, how complete the argument is, you must have a look yourself. Yeah, but he's following exactly your idea. Yeah.
I see. Thank you.
The point is that I mean, you need also it's not only the asymptotic momentum. You also need you know, the phase shifts, right? I mean, these are your sort of new coordinates, so to speak.
Yes, that's right. Yes. Thank you.
May I ask one more question, Abhishek? If there's
yeah.
Sorry, Herbert, this is a slightly vague question, which is, so I'm not aware if there are n-body systems with the following property, but you sometimes talk, at least for two-body systems and smaller systems, of super integrable systems, where the number of conserved quantities is more than n. Firstly, the question is, are there integrable models which are actually super integrable? And secondly, if so, then do some of these things get modified for that, in the sense that you sort of now have even more? So in some sense, you're not even on Toda, you're sort of restricted to even smaller subspaces.
Good question. I just simply don't know. I mean, I never. I mean, you know, the kind of systems which I studied, you always have this phenomena that the number of conserved quantities is extensive, and yeah, it's an interesting question. I mean, one should try. I mean, you know, the rules of the game are sort of pretty much clear, and if I now have a system which has, you know, even more conserved quantities, yeah, I just don't know. I don't know. I never looked at this. At least from the community, which I know, I don't think everyone looked at. Well, you know, one should look at particular cases and see whether there's some interesting structure which appears. Yeah.
Are there? I mean, the general question, independent of hydrodynamics, of whether there are n-body systems which are super integrable. Are you aware of an answer one way or the other? I mean, you know, of course, of the Coulomb potential for two-body system and so on, but there's yeah. So, but it just occurred to me that I haven't seen anything where people have talked about an n more than the dimension, half the dimension of the phase space for n-body systems.
Oh, no, I just don't know. Presumably, I'm not really a sort of a good person to ask, but you know, yeah, I think one you know, one should have a look. I mean, one should see what one can say. I mean, I just want to emphasize that you know, having a look, at least, you know, from this type of experience, really means that, you know, the first thing which you have to understand is, you know, what is the structure of your what people call the generalized Gibbs states, right? I mean, so rather than trying to do some dynamical quantity, which still are very difficult, you see, I mean, nobody shown that, you know, the hydrodynamic equations which I've written down sort of follow from the microscopic dynamics. I mean, that's something which nobody knows how to do. But if one wants to see whether there is some you know, connection to the kind of structure which we discovered in this particular class of systems, I think that the very first step is trying to see, you know, is there something like a free energy, or is there something like a generalized free energy? This would be sort of the first natural questions to ask, right? And then if they turn out to be either, you know, trivial or maybe not so meaningful, then it's not so clear how you actually can continue the program, right?
Thanks.
Rajesh, is there any such system known besides this Coulomb systems? Or
I mean, harmonic oscillators.
Yeah, those two I know.
Yeah, yeah. I think that at least a few body systems. I've heard people talk of some of them, but I can't think of n-body systems. But yeah, I haven't really looked or thought about it. But I think there are, other than the Coulomb and the harmonic oscillator, there are a few other curious systems, but.
Yeah, other questions?
Thank you.
So maybe I'll ask a question. So, so Herbert, I mean, this the Euler equation for this integrable systems, it sort of looks like a Boltzmann equation, right?
No.
And
we had this discussion already at the ICTS, and there were sort of let's see, where do I have this? Yeah, okay. So here, this is no. I mean, okay. Okay, I just want to say that we had a discussion at the ICTS, and then there are sort of somewhat different terminology and sort of opinions. But for me, the crucial point is that I mean, of course, you could say it looks sort of like a Boltzmann equation, but you see, I mean, I mean, the effective velocity is really computed exactly at the space-time point, right? And that's not what you usually do in a. You see, when you think of Vlasov type equations, which are, of course, have a similar structure, right? I mean, now the Boltzmann equation has a collision term, which is strictly local, but you know, that's a dissipative term. So,
okay.
So I would, yeah, no, I don't. So you see, if you want to think about, I mean, you can think about Boltzmann in this way if you want. So I mean, you know, what's happening in Boltzmann in this language is that you sort of start from the ideal gas, which sort of has a trivial hydrodynamic equation, which is a free motion, right? But then you're asking yourself, what is sort of somehow the first order correction to that, right? And then you see that the first order correction comes from the collisions, which are, of course are still a local term. I mean, that's completely correct, but then they sort of, you know, have a slightly different structure. I mean, the collision term has no ddx in front, but it sort of mixes the velocities. Right? So it's not totally unrelated. First, I'm just saying that the way how you write and also the way how you derive. I mean, you know, the central element is that you want to argue that locally you equilibrate to something which has a non-trivial structure, right? When you do the Boltzmann, I mean, then of course you also, you know, locally you just sort of see an ideal gas, right?
Right. Yeah. Okay.
So yeah. So it's okay. You know, names are names. I mean, I'm usually you know, and also they're historical. We would like to see this as a particular case of a hydrodynamic equation rather than of a kinetic equation. But you know, it's not such an important issue. Okay, yeah.
So can I just clarify something, Herbert? So the take-home message is that if you have an integrable system, find its lax pair and look at the spectrum of the lax operator and develop the hydrodynamic variables from there. That's true for all these systems.
No. Sorry if I interrupt you. The lax pair is a very special property of the Toda lattice. You see, the delta Bose gas, there is no lax pair.
I see.
But there is an analog of the density of states. And the density of states is simply the density of the root equations, of the beta equations, which gives you sort of the momenta, right? It's that.
I see, yes. Okay.
So what are here the eigenvalues of the lax matrix, the delta Bose gas, are is the density of solutions of the beta equations.
Okay.
So these are, mathematically two very different objects, right? In one case, it's sort of like a random matrix which has eigenvalues and has a density of states. In the other case, it's a nonlinear. It's a nonlinear set of equations which has sort of input data which are sort of, the bare momenta which are uniformly distributed, and then they sort of generate some distribution on the KJ. So it's a somewhat different structure.
Yes.
There's no. There's nothing like a lax. In fact, lax is I think Toda is the only case where the lax has been used with such kind of with so much success, right? I mean, yeah. No, the lax is special for Toda, but the equation which comes for density of states, I mean that's something which generalizes.
Sorry, Herbert, these quasi-energies, do they have a simple physical interpretation?
Well, let's see. The quasi-energies have a simple... No, not... Well, not... yes and no. I mean, I mean, when you look in the literature, that of course, they are connected. People talk about quasi-particles, and then quasi-particles have a certain distribution which is given by these quasi-energies. So, in terms of quasi-particles, sort of look more like a sort of modified sort of, with the scattering shift modified Fermi gas. That's fine. I mean, so, I mean, not, okay, if you say direct physical meaning, depends a little bit, what you mean by it. I mean, certainly in terms of, if you want to compute averages of physical observables, I mean, you have to go through this scheme here, right? I mean, once you know that these energies is not enough. I mean, and then it's not really, it's very difficult to say, of course, people talk, as if the quasi-energies are the energies of the quasi-particles, right? I mean, this is where this language comes from.
Mm-hmm.
But okay, then you ask yourself, I mean, what are these quasi-particles exactly? And what is their energy? I mean, it's sort of this loose talking, which is, of course, also here you see, I mean, you want to think of this and then it's being modified through this interaction, through the scattering shift. And so I think it's, people who are used to it, it's sort of, it's a common language.
Okay. So these are like energies in the same sense as quasi-particles in the Fermi gas are quasi-particles.
So yes, I think so, yeah.
Okay, thank you.
So if you want to sort of, get a better answer, I mean, you just sort of, look up, sort of a paper, I don't know, look up a paper on the delta Bose gas, and then also talk there about these quasi-energies, and it's a useful language. If you really, it's sort of similar to the quasi-particles are even easier. I mean, what are exactly quasi-particles? If you really try to pin it down what you mean, then you might have difficulties, but nevertheless, it's sort of a useful concept. I mean, for instance, this formula for the effective velocities was first derived on looking at the picture of quasi-particles. So, it's a useful way to think about it. It's sort of something which is sort of as a particle character. And of course, you know, these quasi-particles don't behave like classical particles. They have a different scattering mechanism, you know, which is sort of determined by this two-particle scattering shift. And it's a useful picture, yeah.
Okay, thank you.
So I think, sorry to interrupt, but I think we are running a bit late. So
You are missing.
So maybe we'll stop here. So let's thank Herbert again for a really great talk.
Thank you, Herbert.